Hey, it's Steve. It's April 5th, 2017. It is 16:45. I'm going home from work. Man, the beard's getting long and gnarly. Anyway, I wanted to talk today. I was talking about geologic time, but I'm going to do something different here. I want to talk about how we know the internal structure of the Earth, okay? Because I've seen physicists get this wrong. It's not a guess, okay? Granted, we haven't even drilled down to the crust mantle boundary, and that's not even truly the mantle. I mean, under the crust is a lithosphere, which I guess is technically the upper mantle, but the lithosphere and the crust together are all involved in plate tectonics. So, you know, I guess it's neither here nor there. But it's not a guess, okay? It's not just like, okay, the mantle we know is solid, the outer core we know is liquid, and the inner core, until recently, we thought was solid, but now we know. And granted, the exact compositions are theoretical, but we can run tests in labs and, you know, try to figure this stuff out. But it's not a guess, okay? Guess implies that we just kind of pulled it out of our butts, okay? We know the mantle is solid. It's weird because you see lava in Hawaii and you're like, oh yeah, that's a liquid. Yeah, it is. But the mantle, it has solid liquid properties, but it's definitely a solid. It's kind of like silly putty. You pull on it slowly, you know, pull on silly putty slowly and it bends. You pull on it quickly and it breaks, okay? That's kind of how the mantle behaves. But it is a solid, okay? And the outer core is liquid, okay? And we know this because of earthquakes. An earthquake happens on the Earth, and that will propagate through the entire planet, okay? It could be picked up by seismographs, you know, in other places of Earth, okay? That's what I'm going to talk. There's two kinds of main waves. P waves, which are pressure waves, and S waves, which are shear waves, okay? Now, the P wave will travel through any sort of medium. Gas, liquid, solid, doesn't matter. You know, me talking, I'm propagating a P wave out into the air, okay? The more solid an object is, the faster the P wave moves. Like if I knock on something solid in my ear, I can hear it, but if I were to put my ear to that dashboard and hit it with it sounds louder, and the P wave is moving faster. Air is, wait, I wrote it down here. Sound propagates at about 340 meters per second. At the mantle core boundary, which is also known as the D layer, a P wave can travel 13 to 14 kilometers per second. Okay, so the denser it is, the faster it moves. Okay, now I don't have it hooked. I don't have my phone actually tied in today. So P waves will move through any medium. Okay, and S wave, a shear wave, will not. Okay, it has to be a solid. Dense liquids will propagate a shear wave, but it's really difficult. Shear waves need a solid medium. Liquids have zero to very little shear strength. It all depends on the density. And you mean, you know, we have things in our everyday life that are kind of like liquid-solid mixtures, like Jello. Okay, you know, you know, Jello will propagate a shear wave. It's a solid technically, but I mean, you jiggle it, it moves, okay? So I did this little diagram of mine here to show shear strength in something. The pink here is a glass. This is cross-sectional view. This is a solid. You had solid concrete in a glass. If the glass were to just disappear, the concrete holds its shape. It has strength, okay? In a liquid, we do not. Okay, same thing. The pink over here is my glass. My glass just disappears and the water goes splat. It has no shear strength. Okay, it just, all right. Because what happens in a P wave is, like, you have molecules. It doesn't matter if they're liquid, it doesn't matter if they're gas, if they're liquid or solid. What happens is, if you get something moving, like sound or something, the vibrations, it'll poop, hit the particle next to it, which will poop, hit the one next to it, and just propagate it, so on and so forth. Shear waves don't act that way. Okay? Shear waves propagate perpendicular to that bump, you know, whatever that is, you know, that vibration. Okay? So they're going this way, but everything's moving this way. Okay, so it's going like that. All right. So to solid, a shear wave, if you think of several plates, let's say we have 3, we'll just make this simple, and they're bonded, there's actual molecular bonds between them. If you were to hit the top layer, the second layer is going to move back relative, but eventually it's going to catch up to it, stick out, and it's going to pull the one below it and move that wave forward. Okay. Now, in a liquid, that doesn't happen. You can't, the bonds in liquids are so weak that a shear wave is introduced and they just kind of blah, 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 dissipate, okay? So, what does that have to do with the internal structure of the Earth? Unfortunately, our printer is only printing in black and white. But you see here, this bottom, is a chart. They have epicenter written here. But it's actually the focus. The focus is actually where the earthquake occurs, but most of them that we measure do damage are only maybe a couple miles deep, and the Earth is a lot thicker than that, so it's essentially the same thing. And this shows you how P waves and S waves propagate. Notice S waves do not go through the outer core. That's how we know it's liquid. They will go through slightly because it's a very dense liquid under a lot of pressure. But the P waves, as you can see, they go both shear and, where are you? Both the shear and the pressure waves, the P waves, they go through the mantle. That's how we know the mantle's solid. Well, how do we know the inner core is solid if shear waves can't even make it through the outer liquid core to get into it? Well, like I said, the P waves will, and they'll get deflected slightly as it propagates through. You saw the bends on there. You know, the waves, as they hit a discontinuity, as we call it in geology, they change direction slightly. Those changes in direction help us know that the inner core is solid, because P waves travel almost but not quite straight through. Like if you had an earthquake at the North Pole, the P waves, and a seismometer on the South Pole, the P waves would not reach that seismograph on the South Pole. Okay, they would be close, but not quite. All right, so, well, what are the composition of these things? Well, we can do density tests. That's why we're pretty sure the inner core is pretty much a big ball of iron. It's slightly less dense than iron should be at that depth and pressure, which means there are lighter elements there. And the outer core is assumed to be the same thing. We really don't know for sure, but like I said, you can do density tests and you find out it's basically the same composition as the inner core. In the mantle, we actually do have slabs of lithospheric mantle up on the continents. When mountain building events happen, you get a continent that goes up. Sometimes some of that will be dragged up with it and get preserved on the surface. So we actually do have technical mantle at the surface in places. And also on the ocean bottom, obviously the lava is down coming from the mantle, so, you know, Hawaii. Sorry, I had to shift there. So we do have submantle, representations of physical mantle on the surface. We do not have any core samples. The solid inner core just rotates. As heavy elements decay, keeps it hot, but it's under so much pressure it's solid, and that heat just radiates into the outer core, which is, since it's liquid, convex, which helps drive the mantle. Like I said, the mantle's solid, so although a convection cell in the inner core, we don't really know, may take a couple centuries, in the mantle, it could take millions of years, because the mantle is technically a solid, and we're not really sure if the convection drives plate tectonics, or if actually the cold ocean plates slabbing down and gravity actually pulling it and then letting that new lava at a rift come up is the driving force. It's probably a combination. I mean, the Earth is old. Like I've mentioned before, 3 billion years or 3.5 billion years ago, we did not have plate tectonics operating at all. So, who knows for sure. But I just wanted to explain why we know what we know about the interior of the Earth and how we know it. I just didn't, because I don't even remember what the documentary was. It was a physicist. He has a PhD, but he's a physicist. And when he said, and somebody asked, how do we know the interior structure of the Earth? And he said, oh, it's a guess. And I was like, no! But anyway, I hope you learned something. Have a good day. Oh, by the way, 5th of April, it's 39 degrees out. We've had rain on and off for 2 weeks, mostly on. I just wish this would stop already. All right.